This is part 4 now of phasors and phasor forms for vectors. The phasor form is something that works good when you have sinusoidal conditions for a particular parameter, and usually that parameter is time t. And the relation between the real vector and the phasor form is, here we have the real vector. We're using E as an example of a function of a position vector in time, and that's going to be equal to the real part of the phasor form of the vector, e to the I omega t. And one of the reasons for looking at this, and you can go back and look at the other sections for more details, is, for example, if you take the partial with respect to time of what's in the square brackets here of the phasor form, with the e to the I omega t, you wind up with I omega times the original form e to the I omega t. One of the things that we're going to need in working this example out is the Euler Formula, and that's e to the I theta is equal to cosine theta plus I sine theta. So at the end of part 3, what we had done, we found a real vector. We started out with a phasor form, and then we found this real vector. What we want to do now is we want to work from this real vector back to that original phasor form. So this is what we ended up with in part 3. We have an x component and a y component. And what we need to do is get things in the form of e to the I omega t. So if we look at the x component, we have 10 cosine x, and we can add a imaginary part to it, because in the end we wind up taking the real part. But we want to get to an e to the I omega t, so we add in a sign of that quantity. I didn't fill in the parentheses, but it's the omega t plus phi. And we found in part 3 that phi is equal to the arctan of minus 8 over 6. We'll use that in a little bit. So using the Euler formula, we can get down to now 10 cosine x e to the I omega t plus phi. And we'll expand out that exponent. So that'll be 10 cosine x e to the I phi e to the I omega t. Now what do we do with the e to the I phi? Actually, it's going to be 10 e to the I phi. So here's 10 to the e to the I phi. And that phi is the arctan of minus 8 over 6. So if we think in terms of a complex number, u plus iv, then in the complex plane, with our u-axis and our v-axis, this angle represents phi, and it's the arctan of v over u. And this length here would then be 10. So if we look at that, we can see with phi being the arctan of minus 8 over 6, z would then be equal to the u, which is 6, minus 8, which is the v, minus 8v. So z is equal to 6 minus 8i, and the square root of this, the square root of the sum of the squares of those two numbers is 10. That takes care of the 10 here. So this then becomes 6 minus 8i, parentheses, cosine x e to the I omega t. So now we have the x component in the form that we want. We have a complex quantity here and the e to the I omega t here. Now we do a similar thing with the y component. We take what we have for the y component and we add in this imaginary part. That allows us to use Euler's formula to get an e to the I omega t plus pi over 20. And then if we expand that out, we'll get the factor out front, 1 over x plus y e to the I pi over 20. And then here is the e to the I omega t we need. And we just want to remind ourselves that the real vector is equal to the real part of the phasor form of the vector, e to the I omega t. We have the e to the I omega t in both components. So now we can put the two components in for the Phasor form. So here's the Phasor form. Complex vector is equal to what we've had for x, 6 minus 8I cosine x, x unit vector. And then the y component is this part here. So we have e to the I pi over 20 over x plus y, unit vector y. So that's the Phasor form, and if you look back to part 3, this is what we started out with. So we're back to where we started, and that's exactly what we wanted to do.